less reactive, so that's this one here. But you might have seen also LiAlHOR3. That's interchangeable. Okay. A couple other announcements. I've already explained the content of the exam to you, so I'm not going to spend too much time on that. It's in the outline, and more than a week ago, your boundaries for studying were already defined. The Aspen Lab report, mostly because the exam, and I want you to prioritize studying a few other things. I extended the deadline until the next class meeting, not the actual lab like we normally do, but just please don't be late because we'll have a lecture. We'll hit the ground running. We'll be back to starting fresh again. So, and I will need to start even if you're coming in to turn it in later. So make sure you're on time. I don't accept them late for the reasons that it disrupts the class. So if they're more than 10, 15 minutes late, I just usually put that in the new pile called the late pile. So that's mostly just to avoid any issues. So if the printer's not working, it's not worth going to Kinko's and missing the entire class just to do that. If you email me, give me a heads up, explain the situation, then I can work with you to kind of go through that. If you don't have access to a printer, you can always email me just to prove it was done in time, and then follow up with the hard copy from me. Actually, great. Okay. So that's how you can kind of still get in on the deadline without a late penalty. Is say, well, my printer's gone. My printer's gone out before too. I know how that is. So email me pictures of your whatever you can't. Either pictures of your report or a PDF of your report, and then I don't grade it that way. It has to be a hard copy turn in because I like to see the actual pencil markings from my signatures and all that stuff. But if you email it to me, then the one that comes in as soon as possible isn't considered late unless it's just way past that time, weeks away. So I'm pushing that to Wednesday. I know the exam is the huge priority right now for studying, but I don't get to talk to you on Friday to kind of remind you what to do, or at least not very long, to remind you what to do next before I see you again all the way till Monday then Wednesday for our lecture. So over the weekend, instead of focusing only on the aspirin post-lab, it would be a good idea to probably, number one, focus on reviewing spectroscopy, and I'm going to post the old problem set a little bit modified for your spectroscopy review. Okay, so it'd be good to go through just for if you feel like you don't get enough practice to get from Klein. And I agree, he doesn't actually have a lot of spectroscopy problems compared to reaction problems. If you also feel like you need more work, I'm going to post a link to Web Spectra. So that's what you can review over the weekend so that you feel ready to go in the Monday lab. You're going to be stuck there and feel like you're not finishing if you're not comfortable with spectroscopy. Then, the other thing you should be thinking about is the group project, right? So over the weekend, so between exam and aspirin lab report due, you'll also be wanting to balance working on the group project, reviewing spectroscopy, okay? Modified schedule this week because of the exam, so I'm doing workshop right after lecture as usual. It's kind of study hall style. I'm going to bring some of the old exams just printed out with me so that if anyone wants to go over specific questions, we can. We kind of go around the room on the whiteboard. I don't usually deliver new content just because the Friday folks don't get that, but you're welcome to attend, and whatever comes up, by new content I mean just come up with a new problem. And if that happens where I come up with a new problem because it's inspired then by students, then I'll share that usually on Facebook, so just keep an eye out for that. So that's 9:35, and we go until about 10:30. It's like 55 minutes, but if that room, I can't remember when the next class comes in, I usually hang out there a little longer. So if you're having a class and you want to come after, I'm going to treat that as office hours, and then I have to go to 11. Valley is going to do, she's got some problem sets with Radwan, tutoring workshop. So use that as like your lunch break if you want to keep going, organic marathon today. And then, is that the right abbreviation, CAS?
Yeah.
Okay, yeah, so it's the CAS building and Center for Academic Success. Yeah, so it's the tutoring center, basically. And I have helped them handpick a few problems, so to go over that are not ones we've explicitly done together. Then Thursday, tomorrow, because I'm leaving earlier today, I'm taking some of those office hours that normally would have been during their workshop and putting them on Thursday. So I normally can't come in, like I said, on Thursday, but I can tomorrow. So I'll get here around 9, and I'll stay till 11, and if it gets big, I'll look for another room. I'll probably plan, if no one has any idea what to do, to just kind of share my ideas of good roadmaps with you, but it just kind of is a good way to study, to kind of get everything to gel. So speaking of which, this is kind of a prep for setting up a roadmap. So you kind of make a list. Some people like to make charts or tables of reactions that were covered, okay? And then you can organize them in a more connected way. And so just an example is, Klein's actually already spelled it out. So I don't really explicitly do this with you usually, but in office hours, if no one has anything else to come up with, what I might do is take his, because I would actually write it the same way, and then just connecting it to other pieces. So this is exclusive to chapter 20, but you might want to think, okay, how does that connect to 19, right? So where can I get some of these to convert to something from 19, and where can something from 19 convert to these? And that helps you get a bigger picture for the whole class content, as well as when it comes to a synthesis type of problem. Okay, so the plan for today is I'm going to start, what's this section called? The enolate section. And my goal is to just get through the first reaction, because it's kind of a weirdo standalone that takes some time to go through. And it has some review of the old material. So that's page 86. Once I get through that reaction, or at least most of it, I'm going to pass out a few extra practice problems. I think there's almost too many practice exams for exam 2 online, but if I have them in a neat PDF form, I share them. This is one I realized I think this is actually the most recent one, and I realized I hadn't converted it to PDF to put on Canvas, so I thought, this will be a good one to kind of surprise you with. You guys could work on it today, and I'll post the key probably tonight or tomorrow. We'll see. It would be good for you to have one where you can't just look at the key right away, so that you really have to come up with the problems to work together. So I will pass that out. It's two-sided. It's not the entire exam. It's just some relevant ones.
Thank you.
So the exam wasn't only 2 pages. I just chopped out the ones that were the most relevant. So. Okay, before I move on to the subsequent material, are there any questions? Okay. So, let's see what we have here. I wish I could, that actually worked. I was thinking I wish I could zoom in a little more, but it did. All right, so what we're gonna do is review a little bit. So this is a good time to do that, because if I did this after the exam, you would say, I know this already, this is simple. This would be, I hope. So this enolates and aldols, what's kind of difficult about it is that you're moving away from the functional group center, and you're actually reacting the next atom over. And so that can come up with some kind of interesting products, interesting geometries, and they seem a little less straightforward at first because you're drawing some large molecules. But they're very important because it's another carbon-carbon bond forming reaction. So there's actually 2 sections devoted to these. So we'll take it slow today, because I know your brain's going to be on overdrive, and then on Wednesday we'll pick it up a little. But just as review, we're going to introduce the third mechanism that carbonyl reactions undergo, at least for this class. So we're only really 3 categories that they fit into. We've already done 2 of the 3. So we're just trying to get the big picture here. So if we look at mechanism 1, it says what happens when Z is a leaving group. What is that called? So that's actually what we did in the last chapter. Nucleophilic acyl substitution. It's a leaving group, you substitute. nucleophilic acyl substitution. Okay, so then remember that what we get is, so this is a leaving group, so we could predict the product. We keep the carbonyl unless that nucleophile was RH, and then you keep going to do the aldehyde or ketone reactions, right? Notice all this extra stuff that we're drawing out that we haven't drawn out before. Okay, that's because to introduce this new topic, this is now relevant. In the previous section, this was blocked off with just an R group here. This was not defined. We're expanding this framework by one carbon because when we get to the new one, we're actually looking at this carbon instead of that one. So if you remember, I'm going to do the quickie mechanism that you can do when you're trying to get through predict the product quickly as opposed to a drawn out step-by-step mechanism. So that means we can do attack, open, close, kick. Okay, that's the fast version of the mechanism. So that applied to all the carboxylic acid derivatives. That was chapter 20. So we had acyl chlorides, right? Amides, anhydrides, carboxylic acids, esters, right? Those are all under the attack, open, close, kick. Okay, now a special case, I'm just going to do it in green. If nucleophile equals R and H, then we're going to keep going. Ketone, aldehyde. Go to that one.
Professor Myers,
Yes.
can you zoom in on the
Yes.
Thank you.
So if nucleophile, the new group, was an RH, like suppose you did a Grignard. Okay? Now our product is a ketone. So what do ketones do? They can keep reacting. So as long as there's excess nucleophile, C equals RH, it actually keeps going. All right, so I'm going to put a different, I'm going to use black, I guess. If, no, it didn't work. Let's see. If nucleophile is not a leaving group, so the new group's not a leaving group, okay? Then, in other words, if it is not R or H, it's any of those others, then we keep carbonyl. This is very generic. Of course, there's some little tiny, exceptions and subsections of this, but this is, for the most case, encapsulates all of chapter 20. That's like that's most of the mechanisms of chapter 20 follow this scenario. So you have to make a judgment call. You say, okay, my nucleophile is going to attack, open, close, kick. My leaving group's gone. Now I'm here. That's either an intermediate or the final product. Right? So that's chapter 20 in a nutshell. Okay. So if I go back one, I'm going to illustrate that. Ester. Okay, let's do attack, open, close, kick with diball. We get an H in place of the OR. However, H is on a carbonyl or aldehydes. Arrows can come out of this, connecting us to chapter 19. It can keep going in some other way, right? So, for example, if it's a strong enough nucleophile, you have excess, LAH will not stop at the aldehyde. It'll be there as an intermediate, and then the hydride says, hey, I see that this is an aldehyde. I can keep going because I attack aldehydes. So it turns into primary alcohol. Okay? So that is the essence of pretty much everything on the carboxylic acid derivative roadmap. Okay, so the other mechanism we visited was not attack and open, close, kick. We didn't keep the carbonyl. We ended up with an alcohol. So this is when Z is not a leaving group. So Z equals R or H. Remember, this is our ketone aldehyde chapter. That means you don't keep going at any point because you're already at their intermediate, right? Your ketone or aldehyde, it's something that attacks and opens. That's why you cover ketones and aldehydes first, so that after that, if it's ketone or aldehydes intermediate, you have to decide if you attack again. So we always will get an alcohol in this mechanism. So the quick mechanism to show in only one step is you have to decide, am I in acidic conditions or basic conditions? If you're in acidic, activate the carbonyl first. So this is a simplification of this. If it's not, just go ahead and attack right away. Attack, open, and then at some point, whether you did it first or not, this has to get an H+. So it's attack, open, protonate. So once again, I'm going to say it again, these are not real drawn out mechanisms. This is a shortcut to help you think through a problem without filling in a page of a mechanism first, right? If the mechanism is the goal of the problem, then you got to write all the arrows in every step. If the mechanism is not the goal of the problem, you've got to be using the logic of the mechanism. And this really, I think, helps quite a bit, okay? So what does that mean? We have attack open protonate gives the OH. Then we have our spinach, as it looks like for now, because we don't really know why that's there. It's that clunky rest of the R group that's been defined that way. And then we have our new group, nucleophile. So what was the name of this reaction? This was the first class of carbonyl reactions we covered. What happened there? If you say, okay, if you want to know how to name a reaction, you have to know what happened. So we said, okay, there was a carbonyl, the carbonyl's gone. What happened to carbonyl? One atom of the bond got the H, the other atom of the bond got a new group. Close, yeah, we're getting there. Hydrolysis is similar to hydration, right? So that's one of many, that's actually a subset. This is a more generic class. So hydration, we've done that to alkenes, now we did to 11, we did to carbonyls now. So hydration is a type of addition. We added to a pi bond, so an addition mechanism. Okay, so it's hard to believe that that's probably, I don't know, I'd say maybe even at least 70% of the exam 2 mechanisms in those two boxes. They can be pushed into that category. Anything else that was a little weirder just had extra steps, but it still was a subset of that, like Vidic, had some of its own special steps, but most of them fall in this category. So if you're concerned with attacking the carbonyl, so if you're a synthetic chemist, you're basically like an engineer, you're trying to design a molecule for whatever your target was. If you're a materials chemist, you're making applications for the rest of the world, plastics, paints, etc. But if you're a bio-type chemist, then you're more concerned with pharmaceuticals, any bioactive drugs. But in any case, you design the target molecule first, then you have to plan your synthetic route. And when you plan your synthetic route, you have to take into mind, okay, well, what do I need to do? Do I need to modify my starting material at the carbonyl? Or do I need to modify it even maybe a carbon over, which is this carbon? Okay, and that's suddenly going to be a very important carbon. And the reason the H is drawn out is because we're going to use that H. Okay, so remember that what's over the arrow has been called a nucleophile, but nucleophiles can also act as what?
Bases.
Yeah, bases. So we're going to be thinking of what we've been looking at as a nucleophile as a base. And oftentimes it might be negative. And so what we'll have to acknowledge is that in certain scenarios, instead of it attacking the carbonyl, because I know we have a delta plus here, we also have an H that's quite acidic. Why? Because if you have an anion left behind by taking off that H, then you actually have a resonance stabilized anion. And that's Why is that such a big deal? We rarely take off a CH just out of the blue, unless we have a leading group. That's the only time we did it in 211, just for elimination. You didn't just take off a CH, an H off a C. Not very acidic. It just depends on what the neighbors are to allow it to become acidic. And because of the dipole here, pulling away electron density, this delta 8 plus on this H becomes much more pronounced. So we can actually deprotonate the H only on the carbon adjacent to the carbonyl because it gives us that resonance contributor that stabilizes the anion. Okay, so we have, so notice that Z is not a great leading group. It's kind of an ambiguous statement. So in other words, it's not going to do an attack open close kick. Okay, it's just going to kind of leave Z alone. And we'll give that a broader definition later. But that'll include aldehydes, ketones, and some other groups like esters. So, but it won't be acid chlorides. Okay, so my H is gone. I have a lone pair left behind and a minus. Okay, so this is the enolate. Why is it called an enolate? Well, that's actually a question I prompted. Why enolate? The answer is a little more clear in the resonance structure. So I gave room to describe that later on the next page, so I won't go over it twice. But what we want to notice here is that this is your carbonyl carbon. If we're one carbon away, what would be a good Greek letter for that? Alpha. So this is the alpha carbon. So that's the theme of the enolate chapter, is that the alpha carbon on carbonyl compounds is acidic. The alpha, I'm going to say has an acidic H because it's not the carbon that's acidic. Okay, so we are going to take all of our friends from the last chapter, those molecules, and if you modify the reagent to be a better base than nucleophile, instead of attacking the carbonyl, it's going to pull off an atom from its neighbor. It's going to deprotonate. So it's a simple acid-base reaction, right? So enolate was the answer here, and then I have a space for the question there. So I'll repeat the question. I think I usually have that on the next page. So if everyone has that, I'm going to define enolate with a structure, not really with words. Okay, so I'm going to repeat this. So why enolate? Kind of wanted that there. All right, so I'm going to redraw the same mechanism. Very simple. Deprotonate. Leave the electrons on that carbon. You know, when it's overwhelming to understand what's going on, whenever you see carbonyl, I usually label any alpha carbons right away to make sure I'm not doing this kind of reaction, or to see if I have to rule it out or not. Okay, so my product has, this is the same one I drew previously. I don't have a bond there, but I have a bond there, R. So why enolate? Well, I'm going to draw the resonance structure. Here is the resonance structure that shows why the alpha carbon has an acidic H, because its resonance stabilized anion can form without being as unfavorable as a normal carbon anion. So we have the negative charge on oxygen there when we have a pi bond, and then we have our R groups. Okay, so as a reminder, I'm just going to draw it in green because it's not what we have. We learned the name of this functional group in 211. So what's that called? Enol. It's an alkene alcohol. Alkene with alcohol on it. So ene and then all. Okay, so enolate would be 8 is a suffix that tells you oxygen is negatively charged. Good. So think phosphate, sulfates, all the A's you know, that's because they're oxyanions, right? So if we have a negatively charged oxygen, then we have an enol that with a negative charge on the oxygen, hence enolate. So enolate means alkene, alcohol, and negative on O. So the resonance structure that has the more obvious enolate look to it can be the one that attacks next, because that's the exciting part about this. I shouldn't have spoiled that right away because it is really a big deal. It's like it needs a drum roll. But this can attack because we just made a negatively charged species. So it can be a carbon nucleophile. That's the big deal there, because we can make carbon-carbon bonds. And I'm actually not going to do that, open that Pandora's box today, because that's such an important reaction. I want your full brain. So we're going to get there on Wednesday, but we're going to do just a smaller, more classic reaction that's got its own category, that's still enolate type.
Professor.
Yes?
Can you zoom in, please?
Oops. Yeah, forgive me. I am trying to get the hang of this because I do think it's brighter, but it's going to take me a while to have my same automatic, I almost have like muscle memory of things to do on the document camera. Okay, so we have an equilibrium, and your book is going to, as well as myself, I actually tend to favor this species, but you want to know these are the same, okay? So when you're doing enolate problems, you want to know that this could have been, because resonance structure is the same thing. You could have used this one, which gives it its namesake basically, or this one, which is a little more clear because this is where the new bond sometimes forms, and you can see that right away. So your homework answers will use either one interchangeably. So will I, but I more often do the left one. In terms of the equilibrium direction, this is the same idea as what we learned about. It's a type of tautomerization, right? So remember to convert to the enol, to the keto form. So this would be the enolate form. Oops, I want to do that one. But the keto form is this one. And we learned that ketones, carbonyl bonds, are stronger than CC double bonds. So usually the keto side of the equilibrium is favored, right? But so you could justify using either one though, because they are still one and the same. So I'll answer the question though. So keto is more stable. So ketomono than enolate, which is comparing CC to the CO. Okay, so the reason that this functional group gets its own chapter with the subsequent section, aldols, is because it's a carbon anion and it could be a nucleophile. I mean, that's the whole reason of making them. So to make a nucleophile, you get to make a new carbon bond. You have a carbon nucleophile. All our carbon-carbon bond forming reactions, except for Diels-Alder, use carbon nucleophiles. Diels-Alder is not as an anion per se, right? But if you think about are the first few that we learned, acetylide, C-, right? Grignard is essentially like a C-, same with organo, lithium, gillium. Okay, so Wittig as well, right? There's Witterion. So we have a template that we were able to say, okay, the alpha carbon loses its H, and that's where the negative goes. How do we apply that when we see real R groups already defined? The first thing you need to do in the next section is label all your alpha carbons. So alpha, alpha, alpha. You're going to have more than one usually. And you have to make a smart decision as to which one you're going to use. So I'll call this alpha 1, 2, and 3. And this goes back to a classic 211 Cario problem. There's a base. Which H comes off? So I'm only going to draw one H on each. Who comes off? Yeah, the middle one, because it's wedged between, it's the alpha of 2 carbonyls. Double resonance, right? Whereas the terminal ones, the outside ones, only can have resonance with that one. So if you have a minus here, it can go delocalize there, kick up there, delocalize there, kick up there, right? So definitely the middle one is the most acidic. So I'll write that in words because that's something that you can kind of see how this all is so cumulative in the sense of Cario just comes back. So H alpha 2 is most acidic. And that will no longer be an explicit problem for the most part in this section, unless it's kind of the easy first page of the next exam where it's ranking and sort of, by easy it's not usually that easy, but it's, you have to solve that to start the problem. You have to solve Cario just to predict the reaction, right? So it's not usually going to say, oh, which one's most acidic? It's saying, here's a base, keep going on the reaction, right? So H alpha 2 is most acidic, right? So it's the most resonance. All right, so then we say, okay, here we go, deprotonate, and draw our new product. And that can go on to be our nucleophile. We'll do that later, okay? To be discussed. I don't want to start that yet. But that's the important first step to get down. All right, so my goal for today is to do the haloform reaction. At least introduce it, may not do all variations of it. Because it's really not too, it's a good place to start, it's not too heavy. Haloform, if you think about that word, that'll help you remember what's going on in this reaction, haloform. Wherever you've ever heard a halogen with form at the end. You've used it as a solvent before. Chloroform. Yeah, chloroform. So the structure of chloroform is basically all of the H's on methane, except for one, has been replaced with a C. So kind of keep that in mind as we go on. I'll point that out here. How is this similar to chloroform? All the H's on methane have been replaced with an I. So because you can use chlorine, iodine, and other halogens, that's the X2, it's like Cl2, I2, Br2, right? Because you could use those halogens, it's more generic. Instead of calling it chloroform reaction, or the bromoform reaction, or the iodoform reaction, it's called the haloform reaction.
Professor?
Yes?
Is that structure missing another bond? Or like another carbon? At the end?
The product?
No, up there.
Yes,
The
thank
one
you.
that you-
Yeah. Methyl goes there, good. Okay. Okay, so haloform reaction is halogenating at the alpha carbon. So you could kind of probably see it going there. If we remove the H, it's going to be replaced with something else. The whole point is to make a new bond. This can be done in acid conditions or base, and we use Cl2, I2, or Br2. So the iodoform test is a well-known way to do that. It's old-fashioned, basically qualitative analysis technique before spectroscopy was around. So they would say, okay, what functional groups are in this molecule? And the scientists would go in the lab and start doing tests, like literal test tube tests, not spectroscopic tests. Kind of like you did in your 102 qualitative analysis. You look for the formation of a very characteristic, maybe your flocculent, I forgot what that was, aluminum complex. So, you know, that's why those descriptions are so important, especially historically, is because that's what they relied on. They relied on very descriptive words about the precipitate to say, okay, this means aldehyde was there and alkene was there, right? So in this case, it's actually a very nice reaction. I've seen it done before, and you get a really obvious just powdering out of solution of the halogen. So that proves that there's a methyl on one of the two ketones, or one of the two carbons of a ketone. So if this could be a different R group, but as long as a methyl's on one side, you can lose that carbon. So that's this carbon here. So I'll do that in green since it's a little lighter. That carbon is that carbon. You can lose that carbon as a haloform. So iodoform was the favorite one to do. And what is it replaced with? An O to make a carboxylate. And then you can neutralize to get a carboxylic acid. So that's pretty much understood, is that if you neutralize, you can get to the OH. And often the workup's implied, so you know, if you want to get the carboxylic acid, then you'll add some water or acid and neutralize it. Okay, so pre-spectroscopic times, it was used to just take something that was an unknown structure and prove that it had a methyl ketone. So acetone would do this. Acetophenone, so the methyl ketone with benzene on the other side would do this. And they'd say, okay, at least we know that we have a methyl ketone. Now it's actually used to purposely lose the carbon and replace it and enter the world of carboxylic acid derivatives. So if you want that carbon gone and you want an OH there, then this is a synthetic strategy. All you need is an alpha H. Okay, so note because the alpha H, I'll actually do that here. The alpha H is necessary for that. Okay, so there's the alpha H, went off with the carbon as well as the other groups there. Okay, so let's show how this works. We have an alpha H. Okay, so we have to deprotonate that first. So we can think of the balancing the equations this way. This H ended up over here because it's not here. However, in reality, it goes off with the base first, okay? And then we form the bonds here, right? And then this has to get an H somehow when it leaves, right? So we'll show that. Okay, so first we'll always, whenever we're doing anything in this new chapter, we label our alpha carbons. So on any carbonyl, there's two sides, okay? There's always an alpha 1 and alpha 2. If it's symmetric, then you just got lucky that it was a slightly easier problem, but that's not usually the case because most things aren't that symmetric. Okay, so who has the most acidic proton? Alpha 2, because alpha 1 has no alpha H. You have no choice. So that actually simplified that. You didn't even have to go through your Carrier logic. So we have OH minus. That's our base, right? That's better base than Br2 for sure. So your step is always going to be getting that enolate formed. I'm just going to call this pH since I'm not using that side at all. And have a minus there. All right, so we are going to work through the mechanism shown here eventually. Notice the one above, we have one halogen. We didn't get to the carboxylate. It's because you have to do one at a time. And you can actually do that. You can control it and arrive at one halogen as opposed to all three getting on there. So attack, kick off. So remember, bromine itself is nonpolar, but as it approaches an area of high electron density, it gets polarized. So this is back to a 211 concept when we let it add to alkenes. So as it approaches, it'll polarize. Induced dipole. Remember that word? Induced dipole. It's not a permanent dipole. It's not there unless it's next to something. So that's an important intermolecular force, because a lot of things rely on that. But let's back to the beginning. It's like induced vomiting. You wouldn't have vomited if it wasn't induced, right? Induced dipole. Has to be near, it has to have a cause to be a dipole. It's not a dipole by itself. Okay. Now we have attacked the bromine, kicked it off as a leaving group, and we are going to match our first template. We wanted to show getting one halogen on at a time. It can stop there. So yeah, now I have a halogen at the alpha carbon. So the goal was to install halogen at alpha carbon. I'm going to make another label right here that may be a different color just to draw attention. This is base conditions. We're using a base. And every time we have bases present in a reaction, you usually are introduced to the acidic path as well, for reasons we talked about. In synthesis, other atoms present in your molecule or functional groups might be sensitive to base, so you have to use that route. Okay, so since we showed the base version, we're going to show the acid version next. And I'll stop there where we get only one in, because then it would be good on Wednesday's review. So I'm going to do just the acid analog, and we install one halogen, like this one, as opposed to installing so many that it's a leaving group. Okay, so we'll work our way there. But this is my goal today, is just to get us to installation of one. Okay, acid conditions. I'm gonna write that in green too. Same thing, acid conditions. That means if it's the same thing, I could predict the product right away. I'm more concerned just proving, understanding the mechanism. So, what's the acid? Acetic acid. But my product should be the same reaction, acid catalyst. That means my product should be the same thing. I should have a halogen at the alpha carbon. Okay, so acetic acid, I'm going to write that in words because we will see this as the preferred acid, has the acidic H here, right? So now that you know it's an acid, what should happen first? What do you always do? What did you always do in these last two chapters you've been studying? If you have an acid present and there's a carbonyl. You always protonate the carbonyl. So you might say, wait a minute, we're not attacking the carbonyl. Well, let's just get to why we would do that. All right, so we have, I'm going to draw pH to make our drawing a little shorter. Here's my protonated carbonyl. Okay, everything else is the same. Now I can, because we're in acidic conditions, it's hard to form the anion right away. So I can now look at my alpha H's and say, okay, I remember alpha 2 was the only one with the alpha H. So that's the only one I could take off. Why did I wait till it's protonated to take it off? It's because when you're in acidic conditions, you minimize negative charges. It's very unlikely for them to exist unless they actually have to. Why? Because an acid would attack it right away. Right? So how am I going to minimize a negative charge? Well, you'll see as I get the acetic acid to help me out here. It's a conjugate base. The acetate is present, and now it acts as my base. So not only did I need to do that to avoid too many negative charges, but I'm also creating a base. So deprotonate, instead of landing on the carbon, it's going to land on the bond to draw the enolate resonance structure, right? The one that's more true to its name. If it lands there to make the CC double bond, that kicks this open and we have an OH there, right? Instead of no minus. OH with an OH opened. It's now an enol instead of enolate. Sorry, I combined those. Nothing right there. That was a little too redundant. So the reason it didn't land there is because I drew the arrow to be the bond. So that instead of having a lone pair of the electrons over here, and I kicked open, so I have an enol. Okay, we could say, well, I know enols tautomerize, so I'm going to do that. Well, I hope that we're thinking that, because we never really let enols sit there. We always made them tautomerize. The problem is if you do that, this is the keto form. So it's really a useless part of the mechanism is to force it to tautomerize. So instead, we're going to react the enol while it's in that form. So I'm just going to put this kind of in parentheses, just so you're aware, like, why didn't I tautomerize it? Well, because you don't get to the product. You go back to the starting material to tautomerize. So in fact, you let the enol be the nucleophile for the bromine. Okay, so when you do that, how can we show this without a negative charge? Same kind of way that we did it back in the previous chapter. So you can kick these down, reform the ketone form. So that also has the same benefit as tautomerizing. And you have to release the pi bond electrons and kick off the bromine. Okay, whenever you draw an arrow emanating from the middle of a bond, you have to decide, when I did that, who got this new group that was just attacked? Not there, because that just gained the pi bond electrons. It must be that carbon, because that one has gained nothing. It's only lost electrons, so it must have gained a bond to bromine. So you're basically home there. You just have to neutralize. So what do we have around to neutralize? I would accept either, it's just reasonable bases. This is one of the anions, or the anion we just made there. Okay. So different books choose different ones, and I'm flexible because they're both bases, so the logic's good. I keep accidentally getting the highlighter. That's
Professor?
gonna make the mechanism hard to read. Yes?
Why is the tautomerization arrow pointing to the ketone?
That's the side possible route. So I'm hoping that, I mean, I've had the question before, when we start skipping the tautomerization note or noting it, I've had students say, why didn't it tautomerize? Because you get it ingrained in 211 that enols tautomerize, right? And so, but this does not, but the point of the mechanism is to show how we progress the product. So that actually does not help us progress to do that. So instead, you show it does actually energetically another favorable process, which is like tautomerization. You gain the CO carbonyl back. You just do it by attacking instead of tautomerizing. Okay, so yeah, it's good to emphasize that. I mean, if we were being really technical, we would probably draw like a little dotted arrow, you know? That's kind of like a hypothetical, but we're not showing it. So if I made that arrow dotted, that's kind of what that means. So if you want to do that, you can, so that you don't think that's part of the real mechanism. So maybe even write doesn't happen for this path. What is the reality? It happens, but it impedes the path. But if you were trying to show the actual path, like how did you get there? You did that by not tautomerizing, right? It's like if you're going on a hike and then you see like a really cute furry creature on a fork in the road, but you're really supposed to go back to like a visitor center. And you say, oh, I'm gonna go see what that wildlife is, and you go off to the fork in the road, but that doesn't get you where you're supposed to be, right? So how did you get there? Not by looking at the cute furry creature, because that wasn't your goal, unless that was your actual stopping point. You actually were trying to get to the visitor center. So if you're trying to repeat your hike for somebody, you're not going to tell them to go off the fork of the road, right? Because, first of all, that furry creature is probably gone, but second of all, it'll make their path longer, and they say, why did I come back here and go back and then go, right? So that's what those little turn-offs in those long mechanisms do. When you have acid-base mechanisms, you have equilibria turning off at all kinds of spots that are not your destination. It's good to acknowledge them because it helps reinforce understanding of everything that can happen. But what the goal of showing the mechanisms is only illustrating the entire forward path, not worrying about all the side paths. Okay, so in the future, I'm not drawing this. I just did this for clarification. So it doesn't get us there. Okay, so finally, we're going to deprotonate. I said to use Br minus. And just because it's different, but you could have also used acetate. And we're home to our ketone. Okay? Mono halogenation at alpha carbon. Okay, so I'm going to summarize this before we go any further, or before we conclude actually. So the solvent for the reaction is usually acetic acid. So that's because it's also it's useful in two ways. It's the acid, you need an acid, so you might as well use acetic acid as your solvent. Just an acid plus solvent. You know, we all know acetic acid, it's, basically vinegar. Just depends on the concentration. So vinegars, we've used concentrated, and that's actually pretty corrosive. So it just depends on what the concentration is going for. Okay, so if we are breaking this down into two parts, when we have an acid-driven mechanism, we have the acid catalyzed formation of enol. We basically went from a keto to an enol. We did the other path into taumerization. So they're both called tautomerization, but we never concerned ourselves with going back to the enol because the keto is more stable. But they're both, we basically did that. So we're not going backwards. And then the second part is the enol acts as a nucleophile. That's going to be the theme, really, of the whole chapter, is we get an enol as a nucleophile in this specific reaction to attack Br. So that forms our halogenated product. So if I draw out a different R group, we're about done. This is just an example problem. I think I might save this as a warm-up for Wednesday. So just, if you get here early, have that done so you can check I'm just going to put up the answer. Check your answer. So it's another practice problem with the same reagents. Nothing's different other than the R group. So it's just kind of good to practice with different looking molecules. So you can see that here we had the isopropyl on there. Here we have ethyl. Okay, so any questions on that? Leslie? All right, so I'm going to use the rest of the time to pass out a problem set that we could use to continue on to workshop or office hours. You guys can look at it online. So what I'm passing out is what I'm calling Exam 2 Extra Practice. So it has some true-false questions to help you kind of get an idea of what conceptual things you might want to. I would treat this as kind of like a test, right? Because you don't have the answer key yet. Then we have some fill in the blanks, and then a roadmap. Okay. There's lots of opportunities for practicing these roadmaps. You can make your own. A lot of the old exams and workshops have them. Also, while you're working on this, I'm gonna pass back lab reports. So,
Do you have one?
when I
Do we have to?
graded them, I did them side by side.
How many do you have?
That's why it took a while,
What?
because I didn't, actually integrate until I
Do you have
had
one?
all of both
Yes, they were
sets
the
done.
same.
Okay, I guess pass it.
And the reason I did that is because you kind of handed them in back to back. And, for this time only, I did not take off points on your second one that was handed in. If it was the same mistake, same reason you lost points in the first one. The common one is might be people incorrectly documenting sig figs for their data or not using sig figs properly in calculating. If that happened again, I would mark it. I would take off the points and actually went backwards, you might see that in some cases. If you lost points on both, you want to see, then two different things are going on there. So you want to actually see what that is and use the bottom of that for. Okay, I'll turn the lights all the way on. You guys can, we're just gonna treat this kind of like a workshop primarily. And then, so you can talk, you can look at your notes for this.